Hello, friend. In this video, we're going to continue looking at getting started with, training neural networks on some basic machine learning problems. So this time we're going to be looking at a classification and regression problem. So previously we looked at binary classification. So, if you're familiar, a multi-class classification simply means that we have more than one more than two classes. So for binary classification, we have the true class and the false class. So in this example, we're going to be using the Newswire dataset from the Keras datasets, the Reuters dataset. So in this data set, there are 46 different topics. So it's similar to the previous example. If you watch the previous example, so we're going to have the same representation for the input. These are news articles instead of movie reviews, but they are textual input. So we'll have to do the same transformation that we did before to take our list and transform that into a multi-height vector for our inputs. But for the output, we have 46 different classes or topics, and we're trying to classify each Reuters news article that's input into one of the different topics: finance, sports, politics, and things like that. It's a relatively small training set, so we've only got 8,000, 9,000 training examples, and another 2,000 for testing. So, so I want to kind of go over the basics of this again. We have to do the same representation and the same transformation for the inputs like we did before. The outputs, if you see it, since there's a multi-class classification task, are going to be integers. So instead of 0 and 1, we're going to have a number between 0 and 45 for our index topic. There is also a, like our word index inside of this data set. There is a label names. So if you're interested, you can see what those actual categories are that the news articles were in. So you can see that I think these were all actually just subsets of financial data mostly. So they're a little bit more specific than like sports or things like that. So we'll just reuse our function from the previous examples because we're doing the exact same encoding as before. So I didn't mention it, but we also limit it to the 10,000 most common words. So we're going to end up with input vectors that have 10,000 features coming in. We do have to encode the labels, and we'll use a similar way first here, although I think we'll talk about both of these in this video here. So there's primarily two ways that we could vectorize labels when we have a multi-class classification. We could use the one-hot encoding, same idea as what we're doing here. So that's sometimes called categorical encoding. Or we could just leave the encoding as an integer. So we'll see how that works later on in this example here. So if we want to encode this using one-hot encoding, we need a slightly different version, similar idea, but a slightly different version of our function. In this case, this will encode this is for our output labels here. So we want a result that has 46 values for each one of our samples, where only the one that corresponds to the category is a 1, and everything else is 0. So this is a true one-hot encoding here. So the difference between this and the previous one is that multiple things could be a 1 depending on which words were in the review for the inputs. But this is so that's a multi-hot encoding we had before. This is a one-hot encoding. Only one of the categories is the actual label after the one-hot encoding. So there are, I believe, functions in scikit-learn and like in TensorFlow, Keras for doing this kinds of stuff. So there's a one-hot encoding, the two categorical that our textbook mentions. There's probably like a multi-hot encoding as well if we go and look around there. So we should get the same result using the two categorical here. So with that, we're ready to go off and define our model like before. So just remember, kind of as a summary, we've set up our data. So our inputs are coming in with 10,000 features with a multi-hot encoding, and we're going to be using a one-hot encoding as our labels for the output here. So So this is similar to our previous binary classification problem. The inputs are the same. So, but the outputs, we need to change it. We've only, instead of having one binary label of 0, 1, we're going to have 46 units on the output layer. So you'll see the final dense layer here is going to have 46 units. And we want to use softmax. So if you remember from working on the softmax function, it basically is an activation that outputs a probability distribution over the 46 outputs. So that means that every output, when it goes through this activation function, all the sum of all the 46 outputs will sum up to 1. So you can think of it as a probability space. Okay, so this is the common thing we want to do for a multi-class classification output is use a softmax. So, in this case, it's similar to the previous problem, so we can probably just a sequence of dense layers will work well. But the argument here of why we increase this is that because we've got a bigger output space here, a 16-dimensional space in these intermediate layers might be a little bit too limiting. So we increase the number of units. In order to make sure we don't have too much of a bottleneck. Okay, we'll talk more about that idea of a bottleneck later on. So this defines our model. We're using the basic sequential API again. So we already talked about the output activation function. So before we use binary cross entropy, so there's a similar but version called categorical cross entropy, which you would normally want to use for multi-class classification problems, and we'll continue using the RMS prop advanced optimizer as our optimizer for this example problem here. So we again want to do validation while training. So keep in mind that this data set is quite a bit smaller than the previous one. So here we only take off 1,000 items that we're going to hold back for the validation during the training process. Here, but similar to what we did in the previous example. And then let's go ahead and see how the model does if we fit it for 20 epochs here. So it shouldn't take too long to train it for you. So if we look at it, kind of how it did, we can see the validation loss. But the accuracy kind of comes up to 99% here, or sorry, that's the validation loss. The accuracy is around 70-80% over here. So let's display the learning curves like we've done before to get a better visualization of what's happening here. So again, the results will vary every time you run this because there is some randomness in picking the batches and things. You should see something typically like this. So it's probably beginning to over fit somewhere in this range, so 8 or 9, or maybe a little bit later than that is where overfit is happening. We probably picked around 10 because look at the accuracy. The accuracy does mostly increase up to above 80% accuracy on the validation data till about epoch 10 or so. So somewhere around there, the model is beginning to overfit, and we're getting around 80% accuracy on the validation data that we gave it. So as with before, if we want to just use a simple version for fighting, simple method for fighting overfitting, early stopping, and so if we suspect that 10 epochs is about the best we can do, given this architecture, we can just go ahead and retrain it for 9 or 10 epochs, or whatever we think is the best there, right? So let's go ahead and train it again. So like we did in the previous example here, we're basically saying, okay, so this is kind of going to be our final model. So what you would normally do then is do one final training on the best stuff that you found using your validation data, but do it on all the training data, which is what we do here. But in this case, we're using the early stopping method in order to try and get the best generalization that we can from the network that we saw. And then we evaluate our test data here. So notice on our final evaluation on the test data, we're getting an accuracy of about 80% on the test data. That's what the very last line is here after the 10 epochs of training. So one thing to note about this is, it seems similar as before, but this is actually more impressive than we had on the previous example. Because there's 46 different categories, and the categories also aren't completely balanced here, making it even a little bit tougher, right? But a pure random guesser, as we'll see here, since the categories aren't completely balanced, if you just do a pure random guesser, you actually can get about 20%, well, a little bit under 18% accuracy, right? So just randomly guessing gets 20%. This does better than that. So, this gets 80% with the network architecture that we had on guessing which of the 46 different article types each article is. Okay, and then, real quickly, like before, if you have a model that's working and you're kind of moving on to the production stage, you'd be doing something like using the predict method on an already trained model. So you can see, for example, that we do predictions on the test data again. Everyone has an output of 46, of size 46. So this is just the outputs for the first test sample. Right. So, again, those are all the sum of all these numbers is going to sum up to 1 because we're using the softmax output function. So, normally, of course, if you want to figure out what your prediction is, you want to find the maximum. So in this case, we would want to use the argmax function. So if on your predictions, argmax will basically return which of the index had the highest value, which was 3. So category 3 was what we were predicting as the correct output. That's our prediction. The correct label was 3, so it actually got that one correct here. Okay, and then real quickly, since the textbook went through this, we did mention that you can actually just leave the labels as an integer number. So in that case, you don't really have to do anything with the training labels that you get out of the data set from the Keras data sets. So if you do that, the only thing is you should change your so if you want to use integer labels, you should change the loss function to sparse categorical cross entropy. So that's the one that's associated with integer labels. You'll see you'll get similar results. I think usually you get better results if you use a one-hot encoding categorical cross. You get the same or maybe slightly better, but I'm not 100% certain. You might think, we're still using 46 output, so and a softmax, right? So, but the sparse categorical cross entropy does the right thing in order to take the integer label and calculate the loss compared with a 46 softmax units. So, but yeah, that's not a mistake. You do need to still do 46 unit softmax even if we're using a single integer label on the output here. So let's go ahead and let that train, but you'll see we'll get similar results, around 80% performance on our final test model. So here our training is done again. So the learning curves will probably look pretty similar. So we're maybe overfitting again around epoch 10 or 9, and it tops out just a little over 80%. We didn't retrain it, so maybe this is a little bit unfair here. So we get 78% of the test data, but if we retrain it, we'd probably get the same about 80% as we did with the previous method that we did. So another little word about the idea of an information bottleneck, or the importance of kind of the size of the number of units in intermediate layers. So having a bottleneck can be both good and bad. Right, so you just kind of have to know what the effect is. So, for example, if we make that much more of a bottleneck, in this case, like reducing it down to 4-dimensional, so having 4 units in those intermediate layers, what's the effect that we would see if we do that? so here, okay, just one of the intermediate layers. So the one immediately in between the first one and our output layer, we reduced down to quite a smaller dimension. So it'll be definitely kind of a bottleneck that happens here. If you're overfitting, a bottleneck can be good, but we weren't overfitting too badly here. So if you bottleneck too much, you're going to force it maybe to underfit. So let's go ahead and let this train. So once the model is done training, we can look at what effect it has. We can kind of see what the validation accuracy was. But yeah, if you go back and compare that to the previous, we're 10% on the accuracy lower than what we were getting before. So even though it does look like it's overfitting again, right? But yeah, in this case, the information bottleneck is causing the model not to be able to represent as well. So the performance isn't able to reach the same level as what we had before. Okay, so let's summarize real quickly here. So some things you should take away, remember from this example of a multi-class classification problem using a neural network. So the main difference from the binary classification is that in the last layer, it should still be a dense layer, but of size n, whatever the number of classes is in your multi-class classification. And you should pretty much usually use a softmax activation function, which will give you that probability distribution over all of your n outputs that you're trying to learn for the multi-class problem that you have. You should use categorical cross entropy or sparse categorical cross entropy. You can leave the labels just as integers, but you still want to use the same n outputs in softmax on the last layer, whether you're using a one-hot encoding or an integer encoding. If you do a one-hot encoding and use the categorical cross entropy, you do need to convert your labels to one-hot encoding in order for Keras to work correctly. If you give it that as the labels for the training. And be aware of information bottlenecks. So those can be both good and bad, right? So they can force your model to underfit if it's a bottleneck and your model's not powerful enough. But if your model's powerful enough and it's overfitting, you can create bottlenecks in order to fight the overfitting. So it's another method that you might have in your toolbox when you're at that point and you need to find out how to fight overfitting to get the best generalized model. So that wraps it up for this video. I hope that stuff's useful and hope you'll join me for the next one where we will turn to regression problems.